If you want to find the square of any rational number, most math teachers will teach it to you in two different ways. First, they'll have you memorize the squares of 1 through 10 or so, and then they'll also teach you how to multiply, so you can just multiply out the same number by itself. For a number like 3, for example, both of those methods work quickly and easily, but for a number like 23, they do not have you memorize what its square is, and to do the math for that is complex. And it takes a while to do. Now, what if I told you there was a simpler way to do it, a shortcut of sorts? This shortcut can be somewhat difficult to learn, but so was multiplication back when you learned it for the first time in 2nd grade. And how did you get better at it? Practice and repetition, and the same goes for this shortcut. So first of all, let's lay out all of the numbers between 1 and 20, and below them, all of their squares, respectively. Now look at all of the squares. Remove the ones placed on all of them like that, and as you can see, now for 1, 2, and 3, their squares are now gone because there are only one digit for each, so just remove them from this. Now look at what we have here. If we just examine the string of numbers as it is, you may now realize, like I did, that a complex yet predictable pattern emerges here. We start out normal with 1, 2, 3, 4, with the difference between the next consecutive number being 1. 2 minus 1 equals 1, but then it goes into 6, 8, 10, 12, 14, 16, with the difference between the next consecutive numbers here now being 2. 8 minus 6 equals 2. Next it goes into 19, 22, 25, 28, where the difference between the next consecutive numbers is now 3. 22 minus 19 equals 3. Let's stop there for now and see if we can figure out an explanation for this pattern. For the first 4 numbers, just add 1 for each number. Then the next 6 numbers add 2 to each number. And then for the next 4, add 3 to each number. So, do you up the increment every 4 or 6 times alternating? At this point, it does appear that this is what is happening here. If this is indeed what is happening, when the next section after 28 would continue 6 times. Let's see if that is true. We get 32, 36, 40, 44, 48, 52, and then 57, so yes, this does seem to be a valid repeating pattern of alternating sets of 4 or 6 like functions. Now, what would be most helpful for learning this and remembering this method, in my opinion, is if there was some sort of mathematical formula or equation that sums up this shortcut. I spent a very long time trying to figure out an equation for this, and I did come up with an equation. I'll show that on the screen now. As you can see, it is very complicated, and it is not fully correct, but it is close for high numbers, but unfortunately, as you know, close does not count in math. I wish I could say I figured out a perfect equation for this, but I did not. So I put this equation into this website that lets you put in a math problem here, and let's see what happens. First of all, if this formula was perfect, what would we be expecting out of it? Well, it was supposed to mimic the whole thing with the incremental ranges that I explained first, so we should be able to put in any number for x and get out the square of x without the ones digit, like in my first example. Let's try x equals 12. We get 12.23, which is about 2 off because it should be 14, because it is really 144. For x equals 13, we get 16, which is actually exactly right. 13 squared is 169, so without the ones digit, it is 16. What about x equals 14? It is also perfect at 19, and x equals 15, you get 23, which is 1 off from what it should be. So now you're probably thinking that, like most problems, now the output of this equation would get further and further away from the right answer, but no, because x equals 33 renders a perfect answer again with 108. Amazing. If you want me to make a whole other video about how I came up with this equation and other relations I found with the squares of numbers, then I'll make a video about that when this video here gets 10 likes. Previously, I had planned for this to be the end of the video, but guess what happened? I found another relation that may help you when counting up in the squares of rational numbers. Let me show you. So once again, I'll show the numbers from 1 to 20, and then I'll show their squares below them. Let's say you are listing each consecutive rational number's square. Starting from the square of 1, the difference between that and the next square is the next consecutive odd number starting at 3. For example, 1 squared is 1, and the square of 2 is 4, which is 3 more than 1. So then we have the square of 2, which is 4, and the square of 3, which is 9, and the difference between these two numbers is 5. Are you seeing the pattern here yet? So if this theory is actually true, then the square of 4 should be 7 more than the square of 3, and that is indeed true. 16 minus 9 equals 7. Let's keep it going. 5 squared is 25 and 4 squared is 16, and these two numbers have a difference of 9. So there it is, a pattern. If you start at 1, then 1 squared is 1, 2 squared is 4, which is 3 more than 1, 3 squared is 9, which is 5 more than 4, 4 squared is 16, which is 7 more than 9, 5 squared is 25, which is 9 more than 16, and so on. It just keeps repeating. Don't you love math? I hope this video helped you. Okay, goodbye.